Hi algebra students, welcome to another exciting video. Today's video is going to be on exponential functions. So this is a review. Everything in this video is something we've done earlier this year, and it should just kind of refresh your memory. So the first thing I want to go over with you is just the standard form of an exponential function, which is this f of x equals a times b to the x. And so if you recall, A and B have specific meanings within the exponential function. So A, your A value here, this is your initial value or your y-intercept on the graph. And the reason why this is because the y-intercept, or the initial value, is where x equals 0. And if you think about plugging in 0 for x in this function, so if we do f of 0 equals a times b to the 0, well, b to the 0, anything to the 0 power is just 1. So if this is going to equal 1, then all I'm left with here is the a, right? So then I get that my initial value in an exponential function will always be that number out front that is not being raised to the x power. Okay, so now we still have to think about b. And if you remember, the exponential relationship is repeated multiplication. So the idea here is we're multiplying b by itself x times. So b to the second power means multiply b by itself twice. So b times b. B to the third means b times b times b, etc. So we call this b value here our growth or decay factor. And we're going to get into a little more of the difference between growth and decay in a moment. But the key word here is it is a factor because it is being multiplied repeatedly, x number of times. So now if you take a look at the two graphs, we're going to examine the differences between exponential growth and decay. So if we first look at the exponential growth graph, this is actually a specific graph of the function y equals 2 to the x. And as you can see, this function is growing. As we're moving along the graph from left to right, our values are getting bigger and bigger and bigger. So that is why we're calling it exponential growth. So it should be clear just by looking at a graph. Growth is growing from left to right versus decay. Think about decay as like decomposing bodies. So decay is kind of falling apart, getting smaller, decomposing into nothingness, right? So the idea is we're going down here. And this is actually the equation y equals 0.5 to the x. And the key difference in terms of their equations between exponential growth and exponential decay is that for exponential growth, you need to have a number for b that is greater than 1. Because the thing you're multiplying over and over again has to be greater than 1 in order to produce an increase in values. And then the key to decay would be that we are looking for a decimal or a fractional value that is between 0 and 1. So I'm going to let you guys try out those quick practice problems at the bottom of the front page. And we're together going to flip to the back of your notes worksheet and take a look at 2 example problems. So the first example is an example of exponential decay. And it's a word problem. And it says, Kyla drank tea with 220 milligrams of caffeine. Each hour, the caffeine diminishes by 10%. So already we can start to kind of pick out key information within the scenario, even before we kind of look at what we're being asked to do. So we see she starts by having with drinking tea that is 220 milligrams of caffeine. So that right there is going to be our initial value. Because if you think about it, when time is 0, that's when she's drinking the tea. So that is our A value in the standard form. And then we also see that each hour the caffeine diminishes, and that's a key word because that means it's getting smaller as opposed to bigger, and that's cluing us into this is going to be a decay function. And then how much is it getting smaller by? By 10%. Okay, so now we're going to try to write an equation. And the idea is we want to write a function to model the amount of caffeine in Kyla's system each hour, where t is a number of hours. So if we say this is the function k of t, k is for Kyla, then we know we're looking to write something in the form of a times b to the x. So if I keep that in mind, I know my initial value a is going to be the 220. Now to come up with the b value, I need to use this 10%, but I'm not just going to put the 10 in for b. So we need to think about what does diminished by 10% mean? It means that our total amount of caffeine is going down by 10%. So what's left over after 1 hour would be 90%, right? So 90% is left. And that's actually going to be our decay factor, is that 90%. Because we are interested in knowing what's left in her body, not how much has gone out of her body. So we need to put that in a decimal form. So remember that if you have a percentage and you want to convert it into a decimal, all you need to do is move the decimal point. So in a 90 is like 90.0, and then we'd move that decimal point over 2 spaces, and we get 0.9. So then if we come back to our equation, I'm putting 0.9 in as my decay factor. And now I have my function k of t equals 220 times 0.9 to the t. Now the next two parts of this question are having us use that formula to figure out some information about the situation. So first of all, how much caffeine remains after 6 hours? So that means we're plugging in 6 for t. So if I'm doing k of 6, that would be 220 times 0.9 to the 6th power. And if you have a calculator, you can do this along with me. But as I crunch these numbers, I get 57.67. And then we need to think about what that means. That is an output, and our output here is milligrams of caffeine. The next question is a little bit different. It says, how long will it take for it to drop to 50 milligrams? Okay, so we're trying to find a t value where the output of caffeine is less than 50 milligrams. Well, we just saw that for k of 6, after 6 hours, her body had 57.67 milligrams of caffeine. So we're actually almost to the 50 milligram mark. So this is kind of trial and error, but I'm curious to see if I do 7 hours, will I hit the 50 milligram mark? So I'm just setting up the equation once again, but now I'm plugging in 7 for t. And I end up getting, when I plug this into my calculator, and you can do the same, I get 46.37. That's milligrams, right? So that means after 7 hours, she's going to have 50 milligrams or less. All right, so now let's move on to the next example problem. So the next example problem is an exponential growth example. And it's also an example of compound interest. If you recall that phrase, that's where we're thinking about a bank account. But really, compound interest is just a subset of exponential growth. So we have a scenario where when Jessica was born, her grandparents invested $5,000 in a college fund that gains 8% compounded annually. So I had a small typo in my word problem, which I just fixed, and it will be fixed on your worksheet. But you may have noticed it used to say that gains 8% compounded annually. Now it says 8% interest compounded annually. So it's the idea that it's gaining 8% in value every single year. So if we're trying to write that as an equation, again, I'm thinking about y equals a times b to the x, where a is my initial value and b is my growth factor. So initial value should be easy to spot as the 5,000. And then clearly this 8% is going to have something to do with our b value, our growth factor. But a growth factor, again, isn't just that number 8. So we need to be careful about that. So if we come down to where we're going to write our function, it says write a function to describe the amount of money in Jessica's account A. So we're calling it A after t years. So A of t equals our initial value of 5,000 times. So since this is a growth factor, I'm increasing by 8% every year. So that's like having 108% of what I had the previous year. And then we want to think about that as a decimal, because we're plugging in a decimal answer over there in our b value. So that means our decimal point was right after the 8, and we're going to move it over 2 spots. So when I come over here for my growth factor, I'm writing 1.08 to the t power. And then these next 2 questions are going to be similar to on the previous page, or on the previous example. So after 5 years, how much money will Jessica have in her account? So we can do a of 5, and we get 5,000 times 1.8 to the 5th power. Plugging into your calculator, I get 7,346 and 64 cents. So that's an amount of money after 5 years. And then question C says, how long will it take for Jessica to have at least $10,000 in her college fund? So again, this is trial and error. And since I'm kind of running low on space, I'm going to do this question just off to the side. So we see after 5 years, we were at about 7,000. So I'm going to try plugging in, say, 9 years and see what that gets me. So if I do a of 9 and I crunch the numbers in my calculator, I get $9,995 and 65 cents. No, 2 cents, sorry, 2 cents. So that's super close to being at $10,000, but it's not quite $10,000. So I'm going to try plugging in 10 for t. So let's see, after 10 years. And when I plug that into my calculator, I get $10,794.62. And yes, that is more than $10,000. So now we know it's going to take 10 years for her bank account to have at least $10,000 in it.